Okay, hello AP Chemistry. This is going to wrap up some of the work that we are doing in Unit 5, our kinetics unit. So we started talking about this. My hope is that you were able to look at some of this and understand that we're looking at mechanism information for reactions. And so these are those so-called elementary steps. You will not need to produce these yourself. And in fact, you'll notice over here that these are labeled as either fast or slow. That's also not something that you're going to need to be able to produce. And so I think we had a little bit of a conversation where of all possible reactions, we're really looking at a very tiny subset of reactions. That subset has to have this particular requirement that one and exactly only one of the individual steps is going to be very slow relative to all the other steps. And what we do is we make an assumption that that slow step is the rate determining step and effectively characterizes the rate of the entire overall reaction. And so we are only going to actually talk about a couple different cases even within that tiny subset. The first case is going to be what if the slow step is first, followed by a fast step. I have a variation of that here that has a catalyst. I'll come back to that in a second, but this is still slow step first, so that's one of your classes. The second class of reactions that we'll look at is what if I have a fast equilibrium followed by a slow step, and that's going to be right here. So I'm going to walk us through how we are going to pull the rate law information from the information that you're looking at right now. We're going to do this one at a time. So forgive the kind of low-tech nature of this, but I am just going to start kind of doing some writing here. Okay, first, this is the simplest case. If anything, you could be in danger of overcomplicating these. What we are always going to do is we are going to say the slow step dictates the rate law, and what we're going to do is we are going to write the rate law for the slow step and only the slow step. And in this situation, so the rate law, of course, being rate is equal to K A to the X B to the Y here. So for a generic reaction, we went through and we were really careful to say you cannot assume that those exponents are the same as the coefficients before the reactions. That is a true statement, but you cannot make that assumption that this X is going to be a 1 or something like that when you are looking at the overall. There is a correlation that you are allowed to make. If you know you're looking at an elementary step, that is the simplest possible step that could occur. This is a bimolecular collision that is occurring. If I know that I'm looking at an elementary step, I can pull the coefficient and I can make it into the exponents here on the rate law. So notice the way that this is written, it has the same thing listed twice. That could also be written as a 2 NO2 goes to, and then these guys over here. What I'm going to do is I'm going to write the rate law, okay, the rate constant, NO2, but remember really there's a 2 in front of this one species, raised to the 2 power, okay, and so square bracket for concentration. This is the rate law for this thing because we are assuming that that slow step fully characterizes the entire reaction. And I am done. This is 100% the rate law for that. Now, just to be clear, if the second step were the slow step, I would be really interested in looking at the second step. But we only have these tiny few examples that we're going to do this for. And that was an example of what if the slow step is first. Here's another example of what if the slow step is first. This one I'm adding in here because it also has a catalyst. So here's my overall reaction. It's the decomposition of hydrogen peroxide. And I want to show you that this can also be done with a catalyst. So I minus is my catalyst. And so if I were to write that out, one way I could write that out is I could show my I minus here, the catalyst. I started with it and I'm showing that I also finished with it. Now, it's not incorrect to cancel those out. It's there on both sides of the equation. That gets me back here. So let's talk about both scenarios. Okay, here is the first step. We're being told it's the slow step, so I'm very hyper-focused on this guy. Write the rate law for the slow step. So I'm going to say, this was the previous problem. I'm going to say the rate law is equal to the rate constant times the concentration of H2O2 to the 1 power. I don't need to write that. It's implied if I just leave it, but I'm just going to write a 1. And then I'm going to write my I minus, concentration of I minus to the 1 power. Okay, it's first order in both of these. This is the full and complete rate law for this particular slow step first. Now, you will see a different variation of this type of thing because I happen to know that this species right here is a catalyst. The catalyst is not going to change its concentration over the course of a reaction, because while I do consume it, I also create it back at the end. So this is a constant right here, and it's raised to this constant 1 power. And what I can do is I can fold that inside of this particular rate constant. And I can have a different rate constant. I'm just going to write K prime. That is going to be the rate constant, or maybe I'll put a CAT. I don't want you to think that I'm raising that to the 1 power. So I'm going to write a rate constant CAT for catalyst. It is a different constant. That's the take-home message. But I would still have this species that is still first order. Okay, so all I've done is I've taken this constant concentration of the catalyst and I've folded it in. This would be a different way to write the rate law. This rate constant is going to be a larger value because the catalyzed reaction is going to be faster. All right. So again, very simplistic though. If the slow step is first, all you're going to do is you're going to write the rate law for the slow step. Okay, this one is a little bit trickier, but it actually is covering the same concepts. And so I want to look at this fast equilibrium. What we are saying with a fast equilibrium is we are saying that the forward reaction, one of these and one of these colliding together makes this. And then I can have the reverse reaction, this breaking back apart into those two things. We are saying that the forward rate is equal to the reverse rate. And I can write a rate law for both of those. Okay, that trick is going to come up. This is going to be the difference between the previous two examples. But let me come back because I'm getting a little ahead of myself. I'm going to come back. What is the rate law for this chemical reaction? Well, go find the slow step, okay, and let's write the rate law. So I'm going to say the rate law is equal to K. I'm going to do N2O2 to the 1 power and H2 to the 1 power, okay? I know these are elementary steps because they've been broken out like this, so I assume that I can pull the stoichiometry. It's the only time you can do that. Okay, here's the tricky part. We talked before about what is a catalyst versus an intermediate, and I need you to recognize that N2O2 is an intermediate. I produced it early on in the reaction, and then I consumed it a little bit later. So that is an intermediate. And there's a rule that we're going to follow. And that rule is you are not allowed to have an intermediate inside of your rate law. So what I'm going to do is I am going to get rid of that through an algebraic substitution. And how do I do that? That's when I'm going to go up here to this first step, and I'm going to say the forward rate is equal to the reverse rate. And I'm going to write those rate laws out and set them equal to each other. So here's the forward rate. So I'm going to do of step 1. So I'll put a little circle next to that. I'll put a little 2 next to this guy so that we know that that was coming from step 2, the slow. Okay, so the rate law for the forward reaction, so that's a little f there, is going to be the rate constant for the forward reaction, NO to the 2. Okay, so it's second order, so that thing is showing up 2 times. Now I'm going to have the rate law of 1 still, okay? But this is going to be of the reverse, so that's another r that's sitting there, is equal to the rate constant, r, okay? And if I'm going backwards, it's into O2 to the 1 power. So I'm still up here, but I'm going backwards on this. All right, now what I'm going to do is I'm going to set them equal to each other. That's what it means to be in equilibrium, is that this forward rate is equal to the reverse rate. So these two things set equal to each other. So it's going to be Kf NO second order squared is equal to Kr into O2 to the first power, okay? And sorry I lost you a little bit on my camera. Now again, all I'm after is I'm trying to substitute and replace this thing, this intermediate, which is showing up right there. So I'm going to isolate for into O2 by dividing this over. So Kf over Kr times the concentration of NO, second order, is equal to this, into O2. And then I'm simply going to plug in this expression for that intermediate that's right there. Now this can be a little messy looking. Maybe I'm going to come up here and I'm going to add a little 2 to that, so that rate constant, so that you can track it. Okay, but this is my rate law. I just was trying to figure out a way to get rid of this. So here we go. Rate is equal to K2 right there. Now I'm going to put in these guys, all of this. So I also have a Kf, okay, Kf over Kr that I put right there. Those are from this fast equilibrium. Okay, now I have my NO second order, and that's taking care of that. Now I got to put in this guy, concentration of H2 first order. All right. If you want, these are all constants, so if you would want to recollapse them into a fresh, brand new, I'll put a little O for overall there. You could have the rate is equal to this one rate constant, and then NO second order H2. Oops, sorry again, did it to you. What I did is I defined this new rate constant as a combination of those three. So that's what I was talking about, and I'm just rewriting now. Okay, this is the full shebang here. Okay, and if I come look at what my original problem was, notice the stoichiometry had 2 of those and 2 of those, but the actual rate law does indeed use 2 of those, but it only uses 1 of those. And so, see, here's a great example of, well, you cannot always assume that for the overall reaction you can pull the stoich. Okay. All right, those were the 2 tiny subsets, the cases that we're looking at. If I recap that, what if the slow step is first? Then you just write the rate law for the slow step and you are done. Don't overcomplicate it. What if the slow step comes after a fast equilibrium? Well, you still just write the rate law for the slow step, but then I need you to get rid of the intermediate through an algebraic substitution, and you have to go to the fast equilibrium to find that math. And the key is that you set the forward rate equal to the reverse rate so that you can figure it out. All right, I think that's probably good for this video, and that should wrap up, for the most part at least, AP Unit 5, our kinetics unit.